In the beginning, all information sharing was face-to-face. Here are our heroes, Alice and Bob, discussing their new invention. And face-to-face communications pretty much gets you privacy. You can validate you receiving the exact message that was sent, and just as importantly, you can authenticate who you're talking to.
Computer to computer still needs the same communication assurances. Up till now, we've used cryptography to get privacy. We lock our messages up with a key and feel real secure that only someone with that identical key can unlock them. Next, we're going to look at how to use cryptography to validate that we receive exactly what was sent, and thus identifying if the sent data was modified either by mistake or on purpose during transit or even storage. The public key modules will show how to authenticate your correspondent. As the title indicates, we're going to use cryptographic fingerprints to get this functionality. They're also called cryptographic digests, hashes, and occasionally checksums. A cryptographic fingerprinter will take any message or any file and compress it to about 20 characters. So let's watch Alice use a fingerprinter. Let's say that she has a company that publishes stock picks. Her stock picks don't have to be secret. She just wants to make sure that whoever gets them gets her stock picks and not someone else's. Alice fingerprints her newsletter, puts her stock picks and the fingerprint in an email message, and emails it to Bob. Bob retrieves Alice's stock picks newsletter and fingerprints them with his own fingerprinter. These are widely available. We'll show you some sources at the end of these slides. He then matches the fingerprint he made against the fingerprint Alice sent him in the email. Bob is assured that the message in the envelope was not changed either on purpose or by accident during transit. Just like a fingerprint will uniquely identify a human, this cryptographic fingerprint uniquely identifies Alice's stock picks. But this doesn't get our boy Bob all the protection he needs. It's easy to see why. Some attacker, we'll call him Black Hat, wants Bob to buy his crummy pick stocks. He makes and fingerprints another newsletter, intercepts Alice's, and replaces it with his. Bob would go through that same process as before. He would fingerprint junk, come up with the same fingerprint as what's in the envelope, and the fraudulent masquerade is successfully completed. Many software and content providers put their software or content fingerprints right on their website. So after Bob fingerprints his Alice's stock picks, he checks it against her website, and if it matches, he knows he's got the authentic Alice newsletter. Here's a screenshot of some Adobe fingerprints, and Decrypt also posts our fingerprints. There's even an example to show you how to validate Decrypt's program in the program. By clicking the book icon, we call it our Learn More icon, directly from Cipher a file. Here's another way to stop Black Hat from successfully perpetrating his fraud. Alice takes the shared secret key and fingerprints that key with the stock picks. These kind of fingerprints are called message authentication codes, or MACs for short. Special attention to the word authentication. We'll come back to that real soon. She redoes her email, except she replaces the fingerprint with the MAC that she just made. Bob does the same thing as last time, except this time he adds his copy of Alice and his shared secret key. Only the secret key that he shares with Alice will make the identical MAC that Alice made. It's called a message authentication code because after the matching process, Bob is assured that the same person that had his shared secret key made this MAC. And when Black Hat attempts his fraud again, of course he can't do a MAC with Alice's key, so he tries it with a secret key that he made. Because Black Hat doesn't have a copy of the secret key Bob and Alice share, no MAC he ever makes will ever equal the one that Bob makes. Most major software manufacturers understand the importance of fingerprints and in fact include their own fingerprinters. And you can even find many, many online fingerprinters. And speaking of online, what I found particularly interesting was a hash decryptor. This is how they do dictionary attacks. For instance, use one of these fingerprinters, well, ours for instance, and hash up or fingerprint the word password. Then go and check to see if that particular fingerprint has already been fingerprinted, as well as password 123, password maybe your birthday, etc. Here are some other fingerprint assurances. Cryptographic fingerprints are a one-way function. They're even called one-way functions. That meaning you can't go the other way. You can't reclaim the message or the file from the fingerprint. And it's exactly this one-wayness that prevents Black Hat or anybody else from recovering the secret key that's embedded in the Mac. Additional fingerprint security comes from the fact that the message or file and the fingerprint are a match pair. This means that an attacker can't find any other document that makes the identical fingerprint as this one. Cryptographers often use the words collision or image resistance to describe this kind of behavior. The Avalanche Effect means even a small change in any document makes a big change in the fingerprint, and even the smallest change you make in any document will make about half the bits in the fingerprint change. Fingerprints in Macs are used to detect accidental or intentional document changes. They identify forgeries. Efficiency comes from using a small fingerprint as a proxy for a large document. Security comes from enhancing the fingerprint with a secret key. But we should note that if the message has been corrupted, neither fingerprints nor Macs can recover the actual message sent, but they will identify any attempted forgery. That's quite a big gain. Also, key sharing is a thousands-of-year-old problem. How does Bob know that someone else who has Alice's shared secret key didn't send him her stock picks? He'll never know. Those problems were solved less than 50 years ago by public key cryptography. The most common fingerprinters that you'll see are called MD5 and SHA. MD5 stands for Message Digest, and SHA stands for Secure Hash Algorithm. Although MD5 is no longer considered secure for anything currently being developed, there's still a lot of MD5 fingerprints around on the web. SHA-1 is the current U.S. federal government standard. You might see on the net that SHA-3 is supposed to be used, but so far there has been limited implementation, and in fact NIST itself is still not using it. The last few slides show how to use Decrypt's fingerprint tools. You can get our fingerprinter from the home menu like this. Choose to fingerprint a message or a file, hit the fingerprint button, and out comes MD5 and SHA-1 numbers in both hex and base 64. So for example, paste a message in here, hit the fingerprint button, and out comes numbers like this. What's interesting to note is that the MD5 is shorter than the SHA-1, and the new standard SHA-3 is even much longer. You're encouraged to fingerprint the jar and look on Decrypt.com for your particular Decrypt.jar's fingerprint. You can get Decrypt's 3 fingerprint examples from the DES and AES menu. We suggest to get the most out of them that you do it in the same order that they're shown on the menu, namely first message, then file, then crypt and zip files. And don't forget, Addison Wesley has let us put our book online. These particular chapters talk about fingerprints.